Welcome to an interactive course designed to verify and improve our knowledge of heat treatment. The topic of this course is to explain the issue of nitriding of steels. Nitriding is a process where we change the surface properties of steel by adding nitrogen to the structural lattice of alpha iron ferrite. A number of different structural phases are formed according to the iron-nitrogen diagram. Gradually increasing the concentration of nitrogen in the layer, a solid solution of alpha iron with different nitrogen content of up to 5.7% by weight is formed, a gamma prime phase with a nitrogen content of 5.7 to 6.1% by weight, and an epsilon phase with a nitrogen content of 6.1 to 11% by weight. These three structural phases are commonly found in nitriding. There is also a fourth phase, the theta phase, with the highest concentration of nitrogen, but this occurs only exceptionally. The advantage of nitriding is that it is performed at low temperatures below the temperature A1 from the iron-iron carbide diagram. Thus, there are no phase transformations in the steel itself as we know them, for example from hardening or carburizing. The usual nitriding temperature is in the range of 450 to 550 degrees Celsius. Because the ferritic structure of steel has a spatially centered crystal lattice, there is very little room to place a nitrogen atom in this lattice. However, as soon as the nitrogen atom gets to this lattice, the crystalline lattice enlarges and, as a result, the compressive internal stresses in the steel increase. An accompanying phenomenon is an increase in hardness. Since it is practically difficult to determine where in the layer nitrogen is still located, the nitriding depth of NHD, nitriding hardness depth, is determined according to the rule that the limit depth of nitrogen diffusion is the depth where the hardness is measured by 50 units of HV higher than the hardness of the steel in the core. Regarding the hardness of individual nitride phases, the hardest structure is a supersaturated solid solution of nitrogen in alpha iron. This structure usually exhibits a higher hardness than, for example, gamma prime nitride or epsilon. Therefore, it is not uncommon for the hardness on the surface of a nitrided layer to be lower than the hardness at a depth of, for example, 0.1 millimeter. However, the hardness of the layer does not depend only on the nitrogen saturation. It is determined primarily by the nitride-forming alloying elements. These are chromium, vanadium, titanium, aluminum, molybdenum, and others. The more of these nitride-forming elements there are in the steel, the higher the hardness of the nitride layer. The hardness increases with the content of nitride-forming elements, but the diffusion rate decreases significantly. This means that nitrogen reaches a smaller depth in the same time. The reason is that the alloying elements gradually bind nitrogen to themselves, and the free nitrogen capable of diffusion gradually decreases in the layer. The more of these alloying elements there are, the more significant this effect is. The graph shows diffusion curves for variously alloyed steels and for various nitriding temperatures. The individual curves are calculated depending on the sum of the content of nitride-forming alloying elements in the steel from 1 to 12%. If for pure carbon steel we need only 1 hour of nitriding at a temperature of 500 degrees Celsius to achieve a diffusion depth of 0.1 millimeter, then for steels with 12% chromium, this time will be 8 hours, which is 8 times longer. The nitriding layer usually has several zones. The diffusion layer is a solid solution of nitrogen in alpha iron. No phase transformations occur in this area, only the internal compressive stress in the layer increases due to the lattice gain due to interstitial nitrogen. Towards the surface we see a layer that appears white. This is because it is less etchable than the steel itself. In fact, this is already the layer where the phase transformation and the formation of iron nitrides have occurred. The white layer is therefore a layer of iron nitrides, either gamma prime Fe4n or epsilon Fe2-3n or both together. It depends on the supersaturation of the surface with nitrogen and on the method of conducting the process. The diffusion zone is prescribed on the drawings as NHD according to ISO 15787. The white nitride layer is also prescribed on the drawings and is designated CLT compound layer thickness. The thickness of this compact white surface layer is prescribed in microns. Neither of these layers is self-contained. The diffusion zone indicates that nitrogen diffusion has taken place. The depth of NHD depends primarily on the temperature and time of nitriding and the amount of nitride-forming alloying elements. The surface nitride layer is also the result of the nitriding process, but its thickness depends primarily on the saturation potential of the atmosphere and the thermodynamic conditions of the process. Its growth is exponential, and we achieve saturation of the thickness after approximately 16 hours of the process. In some cases, we want it on the surface, but in others we want to completely eliminate it. However, this is decided by the component designer. We will only consider whether it is feasible on our equipment or not. The Lehrer diagram shows what the saturation capacity of the atmosphere should be to achieve individual types of layers. The saturation capacity is evaluated by the nitriding number Kn according to this formula. It is not important to examine how this formula works. The furnace control system will evaluate it for us if it is equipped with a hydrogen probe. For example, we want to nitride at a temperature of 550 degrees Celsius. If we start a line from this point, we see that it intersects strongly marked areas of transition between individual phases. The nitriding number Kn is plotted on the right vertical axis. If we have the saturation potential of the atmosphere expressed by the nitriding number 10, then we will nitride to form a white surface layer epsilon. If we reduce the potential to 1, then the result will be a white layer of gamma prime nitrides. However, if we want to exclude the formation of a white layer, we must go with the potential even lower. It depends on the process temperature, but the higher the temperature, the lower the potential the nitriding number must be. This is already difficult, because in conventional nitriding in ammonia, we need to add hydrogen to the atmosphere. This is usually solved by obtaining it by thermal dissociation of ammonia in an external cracker. However, if we do not have a cracker, we cannot get into the region with Kn less than 1. If we are not sure and do not want the nitride layer to be too saturated with nitrogen, or we do not want this surface layer of nitrides at all, we can use a suitable combination of saturation and diffusion periods. Single-stage nitriding in ammonia can be excluded. The surface is saturated directly proportional to the ammonia content and its thermal dissociation depending on the nitriding temperature. This process can be controlled only to a limited extent. Two-stage process control in combination with ammonia and a cracker allows to reduce Kn below 1 and to continuously regulate the nitriding number values. The addition of hydrogen from the cracked ammonia reduces the nitriding number. Two-stage process control, according to the Nitrix methodology, combines saturation and diffusion periods. There are two options. The first saturation period is obvious and is identical for both variants. The second period can only take place in pure nitrogen, when the saturation potential is 0. This period can be at any temperature, but it must meet the required diffusion profile. Since the nitrogen molecule is of a size that cannot diffuse into the steel, this phase is essentially a diffusion period in a neutral atmosphere without the addition of nitrogen. The second option is to increase the temperature in the ammonia environment, which automatically increases the dissociation of ammonia and at the same time reduces Kn. However, it should be noted that in the acceptable temperature range up to 600 degrees Celsius, Kn does not drop below 1. In no case can nitrogen be added to ammonia. Paradoxically, adding nitrogen increases the nitriding number Kn. If we want to use only pure nitrogen for the diffusion period, we have to separate the two gases. The last option is the zero-flow process from Secco-Warwick, which works by filling the chamber with ammonia and allowing it to consume free atomic nitrogen without the introduction of new gas. Only when Kn in the chamber drops below the set value is ammonia replenished. There is an AMS 2759 Part 10 standard that directly specifies how to work with two-stage processes. Nitriding processes are split into Class 0, Class 1, and Class 2 groups. For Class 0, the white layer of nitrides is not allowed at all. For Class 1, the white layer is allowed in the range of up to 13 microns, and in Class 2 up to 25 microns. The table then contains the values of the nitriding number for the saturation period and for the diffusion period. In the first phase, the nitriding number is applied, for example, for steel H11, which the steel 1.2343 according to DIN, in the range of 5 to 15, and in the second only 0.3 to 0.8. The table also shows that nitriding without a white layer is practically impossible for carbon steels. To realize the complexity of the process, we need to know that undissociated ammonia has a nitriding number of infinity, and ammonia that is 100% dissociated has 0. This table shows what the nitriding number Kn is depending on the degree of ammonia dissociation when we only release ammonia into the retort at atmospheric pressure. Here we can see that for 100% split ammonia, Kn is 0. For 5% dissociation, it is 4.14. If we try to limit the nitriding number by adding nitrogen, it is a dead end. This can be seen in the second table when we insert 60% ammonia and 40% nitrogen into the furnace. The effect is quite the opposite. The nitriding number rises, does not decrease. And at a dissociation of 5%, it is 5.34, higher than in the previous variant with 100% ammonia. This is due to the fact that hydrogen in the atmosphere has decreased and has been replaced by nitrogen. If we draw it on a graph, we see it even more clearly. On the left is an atmosphere of pure ammonia with varying degrees of dissociation, and on the right is an atmosphere with 60% ammonia and 40% nitrogen. The partial pressure content of hydrogen was significantly reduced by the addition of nitrogen, and the nitriding number increased proportionally. The only way to reduce the nitriding number of Kn is to increase the hydrogen content in the atmosphere. The graph shows the effect of adding 50 millibars of hydrogen to the atmosphere with 950 millibars of ammonia. With 5% dissociation of ammonia, Kn drops from 4.14 to 1.7. But to get Kn below 1, we need to increase the dissociation to at least 12%. But this is not very possible, because we would have to increase the nitriding temperature. However, according to Lehrer's diagram, a higher temperature no longer needs Kn1, but, for example, at a nitriding temperature of 500 degrees Celsius, only 0.3. So we get into a vicious circle. Without additional hydrogen or an external ammonia splitter, we will not be able to control the potential of the atmosphere in the range of values less than 1. But in reality, we do not have to deal with this problem. We only need to have a device that has the appropriate gas flow meters, a hydrogen probe, and a simulation program, which is usually included with the furnace software. They will solve it for us. In some cases, especially in relation to nitrocarburizing, final oxidation of the surface is required to form a thin layer of iron oxides Fe3O4. This figure shows the nitriding or nitrocarburizing process, and on the right, the coloring of the surface step by step. The last step of the process is oxidation with the formation of a layer of 1 to 3 microns of iron oxides. Oxidation usually takes place in water vapor, in air, or in dinitrogen monoxide. The black layer has excellent corrosion resistance and at the same time a decorative appearance. This process is now used to mass process parts for the automotive industry, such as brake pistons or ball joints. According to Euro 7, brake discs and brake pads made of gray cast iron will also be modified in this way in the near future. Like all other metal finishes, nitriding or nitrocarburizing technologies are sensitive to surface cleanliness. Inappropriate or imperfect washing can completely eliminate the penetration of nitrogen into the steel surface. The picture shows that if we use cutting oils and they remain on the surface, nitriding may not take place at all, or only partially, and the surface will be stained. Similarly, however, these are surface stresses created during machining. This figure shows the difference between the uniformity of the nitrided layer without annealing before the nitriding process and with stress annealing. A special problem of nitriding or nitrocarburizing is the masking of the surface where we do not want a nitriding layer. These are both functional surfaces, or in many cases, there is a requirement to protect threads in order to maintain their toughness. With plasma nitriding, it is simple. Where there is no discharge, there is no nitriding. However, in the case of classical gas nitriding processes, we must take into account that at atmospheric pressure in the furnace, the gas has such penetration that it is very difficult to create mechanical masking. That is why protective coatings are mainly used. Copper or ceramic pastes are typically used for nitrating in plasma, or tin-based pastes for nitrating in gas. Because even protection has its pitfalls, it is necessary to follow the instructions for these products exactly. The surfaces to be nitrated and those not to be nitrided must be marked on the drawing by the designer in accordance with ISO 15787. It is then up to the heat treater to cope with this requirement. For nitriding or nitrocarburizing, we mainly use the following technologies: gas nitriding, low-pressure nitriding, plasma nitriding, and salt bath nitriding. Each of these processes has its advantages and disadvantages, as well as its pitfalls. Gas nitriding equipment may look different, but the principle is still the same. These are furnaces with a gas-tight retort, with external heating either by natural gas or electricity. The furnaces are either vertical or horizontal. The basis of the furnace is therefore a retort, usually made of high-alloy chromium-nickel steel 1.4581. Inside the retort is a circulation insert, directing the flow of the working gas, and supports for the batch. Heating is placed around the retort, either with gas burners or electric. The working gas itself is fed into the working space, and its flow is accelerated by a circulation fan. However, since ammonia is used, and not all ammonia is decomposed into nitrogen and hydrogen, there must be a device at the outlet of the furnace that additionally decomposes this residual ammonia before it is released into the atmosphere. The device has one more fan. This allows for accelerated cooling of the batch and retort after the process with a nitrogen stream. The disadvantage of this solution is that each cycle we have to heat and cool a retort weighing almost 1,000 kilograms. This type of furnace has a high energy consumption, 30% higher than in furnaces with direct heating and nitriding under reduced pressure. Gas nitriding is a process with extensive application both because of the creation of high surface hardness and corrosion resistance. Since it takes place at relatively low temperatures, Low deformations are also an accompanying phenomenon. The advantage of this process is the high gas penetration between parts, which is why it is advantageously used for batches of small goods, where the positionability of parts can be problematic. It is currently applied to various structural parts, gearbox parts, shafts, or tools. The versatility of this technology is also in the fact that we can nitride both small and oversized parts. Another nitriding process is the so-called low-pressure nitriding. It is a technology supplied by the Force BMI company from Lyon, which is in fact also nitriding in gas, although at a total pressure of only 300 to 400 millibar, equivalent to 30 to 40% atmospheric pressure. The low-pressure nitriding process is implemented directly into a vacuum tempering furnace with direct heating, and is adapted to work with gases such as ammonia, dinitrogen monoxide, and nitrogen at the above pressure. The working gases are fed directly in front of the convection fan, and thus ensure a good distribution within the work area. In terms of results and reproducibility, it is a very good solution that, like all methods of nitriding, has certain pitfalls. Considering that atomic nitrogen for diffusion is obtained by reactions through iron oxides, this process cannot be used for nitriding for duplex coatings. However, it is a suitable process for general use, especially for nitriding hot work steels. It is proven and gives very good results for nitriding tools for extrusion of aluminum profiles, but it is also used for post-oxidation of part of die casting dies. It is possible to nitride parts without the presence of a white layer of nitrides, but only for alloy steels, such as steels for hot or cold work. Nitriding in plasma is another process used for nitrating steel components. Its principle is based on the fact that in an anomalous electrical glow discharge, we are able to split nitrogen molecules into atomic nitrogen capable of diffusion almost independently of temperature. The processes take place at a very low pressure of 1 to 5 mbar and are characterized by vacuum with high process purity. In this type of process, the use of ammonia can be completely excluded, and the processes are therefore much more environmentally friendly than in gas nitriding. There are several versions of this technology. All of them are based on a vacuum vessel, where the nitrided parts themselves are on the cathode. The vessel of the plasma nitriding device is the anode. The devices can have a cold wall, a heated wall. They can have a DC cathode voltage source rectified from the mains voltage with a frequency of 50 Hz, but they can also be high frequency with a variable pulse, usually up to 1 kHz. A special case is the devices with the so-called active wall, where the actual discharge that splits nitrogen is in the form of a circumferential network in a vacuum vessel. Nitriding usually takes place in a mixture of nitrogen and hydrogen gases. Since we are not dependent on their ratio of 1 to 3, as we know it in ammonia dissociation, we can control the saturation ability of the atmosphere at will. However, since a hydrogen probe cannot be used in a vacuum, the criterion for the saturation ability of the atmosphere is the partial pressure of nitrogen. We can already measure it, for example, by combining partial pressure measurements with a quadrupole mass spectrometer and using mass flow meters as an active element. With this system, we can control the working pressure of nitrogen in the atmosphere in pascals. Due to discharge dissociation, atmospheres composed of pure nitrogen and hydrogen gases are as efficient as ammonia-based atmospheres. The table shows that in all cases, we can obtain roughly the same amount of active gas particles from the working atmosphere. The advantage of nitriding in plasma is that not only thermochemical reactions are involved in the process, but there is also a physical effect. By operating at a high cathode voltage, usually up to 1 kilovolt, the particles ionized in the glow discharge are highly energy efficient. In combination with the reducing effect of pure hydrogen, there is an excellent ability to deoxidize the surface and remove surface impurities. Plasma nitriding also has its drawbacks. It is primarily a shape dependence, where it is sometimes difficult to nitride, for example, deep holes or cavities. This is due to a parameter called the mean free path of the particles. Depending on the mass of the gas particle, ions, and its energy, the effect shown in the picture may occur, where the particles fly over the hole and do not nitride. Another disadvantage is that the parts for plasma nitriding must be precisely positioned, and there must be a gap of at least 10 millimeters between the parts. The effective use of the working space will therefore be lower than in the case of nitriding in gas. However, the great advantage of plasma is the masking of surfaces that we do not want to nitride. A situation where we do not nitride surfaces where there is no discharge can be used. For example, we have a shaft, and on it is the surface that we want to have soft, without nitriding. We put a steel ring over the part of the shaft that we want to protect. It will be nitrided, but the shaft surface covered by it will be untouched by nitriding. Plasma nitriding is the only type of nitriding process that we can use for nitriding for duplex layers. That is, if we nitride the surface as a substrate for the subsequent application of a thin layer of titanium nitride, DLC or other type, using the PVD or plasma-assisted PVD and CVD method. The last technology we will mention is salt bath nitriding. It has its historical application, however, due to the fact that it is based on cyanide salts. The ecological problems associated with this technology lead to its gradual decline. In this table, we see the available processes and their indicative parameters. The course of nitriding is over. It includes my many years of experience and practice. However, the issues can be very complex and extensive, and may not exactly match your experience. If you have any comments or suggestions for improving the course, please send them to the contact listed. My goal is for the courses to provide essential information for heat treatment employees at all levels so that they can continuously improve. The level of content is therefore adapted to allow both existing employees and new employees who do not have knowledge in the field to take part in this course. Based on these comments, I will improve and expand the courses so that they are a real benefit to everyone. As you have probably noticed, the course was not voiced by me, but by the great speech generator 11 Labs. Thanks to him, my English will also be understandable. So thank you also to Bill and his voice for his contribution to the field of heat treatment. What you saw as a video on YouTube is just a picture of what is created in Adobe Captivate as an e-learning course. It is available on my website, jstconsultancy.cz. You can access it for €20 for 1 week, €40 for 1 month, or €60 for 1 year. The course is created in HTML5 format. However, it can also be exported to SCORM 1.2 format, which stands for Shareable Content Object Reference Model. Other formats are possible for different LMS systems. You can order this form at my email address, and you will receive the complete course in HTML5 code and a perpetual license for €200 per course. The compressed zip file will be 50 to 200 megabytes in size, depending on the content of the course. You can then install this file in your corporate cloud or in Moodle LMS 5.0, on SharePoint or in the HR module of your ERP system, such as SAP, which can communicate with a learning management system, LMS, that meets the LMS specification. In this case, you will be able to prepare a training plan for each employee, including an evaluation of its implementation and success rate. Each course contains a test with many questions, and the output is a certificate of successful completion of the course. You can archive these certificates and use them for employee motivational rewards. The advantages of e-learning are obvious. The employee does not have to go anywhere. They can complete the course anywhere, on a computer, tablet, or even a phone, at work, on vacation, or even at home. And you will be sure that they have the necessary knowledge to understand what is happening in the heat treatment operation. I do not know of any disadvantages, so I just hope that these courses will serve you and be useful to you. And what is my vision for the future? You can see this in this process map. So far, 16 have been created in Czech and English, and I will gradually add new ones, depending on their importance in the life of the heat treatment operation. I don't know if the courses are perfect, but I'm sure it's a promising form of education that we shouldn't ignore.